Hello everyone, welcome to this week's video. So this week you learn about regression and you will actually run regression models. And I want to emphasize that learning and running linear regression is very important to successfully complete this course because all the complex models that we will learn and run later on, mediation and moderation models, are all based on linear regression, is general linear modeling. So I strongly encourage you to look at the course materials multiple times and watch this video multiple times to have a better understanding before we move on to more advanced models and modeling. And please contact me if you have any questions, because it's very important that you actually understand how linear regression modeling works before we move on. Okay, so in this week's practice and application, you will run correlation, simple regression, multiple regression, and statistical stepwise regression using two data sets. The first data set is the data that you saw on this week's slides, class material. And the second file is the file that we've been working on that we will use for our final project in this class. So let's start with the first one. Let me download these two files. And as we have been doing, what I'm going to do is copy and paste these files to my documents folder. So I'm going to copy and paste these two files into my documents folder. Okay. And that way, if I refresh this files window by clicking the home button, I will have these two files showing on RStudio window because I pasted into the documents folder, the default folder. So let's first work on correlation and scatter plots. If you remember from the slides, I have very overly simplified the steps of regression. The first step is to fitting a linear line on a scatter plot for the variables. And second is to compare the linear line with the mean, which is done by looking at the overall model f-test ANOVA table, and then and also looking at the R-square value of the model. And then the third step is to evaluate each predictor's effect on y. That is by looking at each predictor's coefficient value and looking at the t-test significance. So we will go through all of these steps, and the first step can be done by working on a pairwise correlation scatter plot among the variables. So we need the read Excel package that is already installed on my RStudio, and the GGally package is used to visualize correlation matrix. I already have that also. So if you don't have them, you can copy and paste everything and run it. But I'm just going to copy and paste it from here because I already have those packages installed. So let me do that. So I'm going to load the read Excel package and the visualization package. And then I'm going to designate my data file. My data file is going to be the Excel file name like this, the one that we downloaded. The variables that I will use for correlation are listed here. The 8 variables that we've been working on throughout the semester, right? And then I'm going to designate that I want the correlation data from among our within our data file, the 8 variables I designated, and I'm going to require a correlation data. I'm going to call that a correlation data. And then I'm going to run correlation. So COR is the correlation command for R. And to run the correlation data, I'm going to use pairwise complete observation setting, and it's going to be a Pearson correlation. That is the most widely used correlation. And then the analysis of the correlation among the correlation data that I designated by the 8 variables is what I'm going to, and we're going to call that the correlation matrix. The output of this correlation analysis is the correlation matrix. So if you see here, then I'm going to ask R to print our correlation matrix, and then ask to visualize. So GG pairs is obviously the GGally package command, right? So let's see what it will give me. So it's pretty obvious that it will give me a correlation matrix and visualization of pairwise correlations. I'm going to run this, and then it gave me a correlation matrix among the 8 variables, and it also gave me a pairwise visualization of the 8 variables. So you can see that each variable fairly has a normal distribution, and it looks like correlation between current salary and the beginning salary had the highest correlation, the 0.807. But these are both predictors, right? So based on the slide materials that you have read and learned, we can kind of anticipate that there will be a high multicollinearity issue maybe between these two variables. And our outcome variable is job satisfaction. So we're interested in the correlation values between job satisfaction and all the predictors. Among the predictors, it looks like job performance had the highest correlation with job satisfaction, 0.673. And if we look at the scatter plot between job satisfaction and performance, let's look at performance and job satisfaction right here. This scatter plot is a visualization of this correlation value of 0.673. It shows a linear relationship to me, right? It looks like a linear relationship, so I'm very happy with that. And let's see. And obviously, the highest correlation, current salary and beginning salary, had a very clear visualization. Let me kind of enlarge this. Yeah, so we have a better look at it. It has a clear linear relationship, right? And this was the second highest correlation. And there's a negative correlation between job satisfaction and stress, right? Stress and job satisfaction. That value was minus 0.470. So you can see that we can have a good understanding among the variables' linear relationship by looking at the scatter plot and the correlation values. If the scatter plots are showing a U shape or a log linear or exponential kind of scatter plot, then maybe running a linear regression is not a good choice. But looking at our data set, it looks like the data are fairly in a linear relationship, so we're happy with that, and we're moving on to step 2. Before we move on to a multiple regression, let's run a simple regression between the highest correlation with job satisfaction, which was with performance. So this is running a regression model, and the linear regression model is we're predicting job satisfaction using performance, using our data set. We already designated our data set right here. So after we ran this linear regression model, then we're going to ask R to report a summary of our regression model. This is the command to do that. And then we can also create a scatter plot, which is additional activity. And I will show you how that works. So let's copy and paste everything here from line 20 and run it. Oh, I already have ggplot2, so I don't need to restart and install it, so I'm just gonna ignore this. So if you already have ggplot2, you might just put a pound sign in front of it, so it will just load the ggplot2 already in your library. So this is the result when we ran the simple regression just between job satisfaction and job performance. You can see that the overall model, the F model, was significant with a p-value with 16 zeros before these two value. So it's very significant. And the performance, the unstandardized value and the standardized values show unstandardized value and the standard error show that t-value was very significant. It has 16 decimals. And if you have noticed, in a simple regression, the t-test and f-test is always shows the same significance. If the t-test is significant, the f-test is significant because it's just two values. And if you remember, the R, uh, if you remember and look at our correlation value between job satisfaction and performance, it was 0.672, right? The R square is basically the square of this. If you square 0.672, it's gonna be 0.4523. So that's really simple calculation in simple regression. What we created using the ggplot2 is based on the scatter plot, the blue line shows the best fit line, the linear line based on the ordinary least square method. And the shaded area is the 95% confidence interval area. So within a 95% confidence interval prediction, 95 out of 100 times in our population, the linear line will range from this gray area to this gray area. So this one and this one. So it's represented as a range. If we had more errors, then this gray area will be wider, right? If that's the case, we're not that much confident that it will be significant. But here we have a pretty narrow green area. So within the 95%, we're pretty confident that our linear line will be quite steep enough to be significant. So that's what we can see with the simple regression. And you can have a good idea about how fitting the linear line to a scatter plot and then interpreting the overall model and the individual model makes sense. And so please read the interpretation of the output here before you move on, because it shows that how the regression formula is calculated based on our analysis, our data, and the performance p-value here is much smaller than 0.05. So we can say that this is a statistically significant predictor of job satisfaction. And then we can look at the R squared value that 45.23% of the variability in job satisfaction is explained by job performance. And based on our criteria, our rules of thumb, is a moderate to strong relationship. And adjusted R square, we're going to use this to compare multiple regression models later. And the F statistic is very significant. And residual, if you remember the assumption of regression, the residual distribution has to be independent and identically distributed. So this is one number that kind of gives us some information about our residual errors, but that is kind of beyond the scope of our class. In our class, we're going to just assume that our data are good enough to run regressions. But if you actually work in the field and if you run any linear regression models, you got to check the residuals. Based on data, our data looks fairly linearly distributed just looking at the scatter plots, so I don't worry too much about that. So next, we're going to run multiple regression models. I'm going to start from line 42, copy and paste the multiple regression command here. So here we included all 5 predictors, right? Beginning salary, previous experience, current salary, performance, and stress. We have 5 predictors predicting job satisfaction. And we're going to call this linear modeling multi-regression model. And based on this linear modeling analysis, we're going to ask for a summary of what we called multiple regression model. So I'm going to drag these and run it. And you can see that the values are identical with the slides that you've seen in this week's course materials. So we can see that while if you look at it, while most of the correlations were significant, bivariate relations were significant, one of them, the beginning salary, became insignificant. That is because beginning salary and current salary share a lot of common variance, the shared variances. They share a lot of variances together. So one effect got diminished. The unique variance left from beginning salary was too small to be significant. Current salary was still a significant predictor, even after holding beginning salary constant. So if we look at this, we have job stress, job performance, current salary are all significant, right? If we look at the estimate values, we can see that now holding all other variables constant, job stress had the largest absolute value when predicting job satisfaction. So that's very interesting because if we look at stress, the correlation was smaller than current salary or job performance, right? But when we held all these variables constant, the strongest predictor was stress. It had the smallest p-value as well. So when you choose the strongest predictor, there is no absolute answer because a lot of discretion is based on the analyst's decision. But you can look at the largest coefficient estimate value, or look at the p-value, or consider everything together, starting from bivariate relationship to multivariate relationship. So I'm very excited about this result because I found that it's not just giving good salary and performing well in the job setting. We also found that job stress actually was the strongest predictor when holding all other variables constant. So if a person has the same level of beginning salary, previous experience, current salary, and performance, what dictates the most was job stress. Next was job performance, very close to job stress, right? So people have to feel a sense of self-efficacy to feel happy with their jobs. And current salary is also, of course, a very important part because if you're performing better than others, and but if you're not paid well, the person will not have a high job satisfaction, right? That makes sense to me. So we ran a regression model, a multiple regression model. We looked at the scatter plot. Then what we do is look at the overall model The F statistic was significant with a lot of decimal points before numbers. And the R square value was 0.652. That means that the 5 predictors explain 67.52% of variance on job satisfaction. That is larger than just one variable. When we just put one variable, it was 45%, right? Now it's 67%. Then our next question as a data analyst would be, what is there a more parsimonious model to explain job satisfaction? That means that the rule of parsimony, Occam's razor, is finding the most parsimonious explanation to explain something, because if you can explain something at the same level with smaller variables compared to others, then there's no need to look at all these other variables, right? If it is truly explaining similar or same amount, right? So based on that, scientists like to follow the rule of parsimony to kind of find the most economic model for us to use. And luckily for us, there's a statistical solution for that, and R runs this for us. So from line 48, I'm going to designate what is the best multiple regression model by using a stepwise regression. So this is the stepwise regression command. And stepwise regression will be ran based on the multiple regression model analysis that we have ran. And the direction will be both. So we can start by including the largest predictors. We could also start by deleting the most least predicting variables. So there's a forward and backward methods, but we're going to use both. So that is a lot of widely used stepwise is a widely used statistical solution to find a parsimonious model. So let's run this, and I will help interpreting this for you. So when I run this, so let's look at from here. What this results tell us is that when we include all the 5 variables in our multiple regression model, the AIC, we want the smallest AIC value to decide what is the best parsimonious model. Our AIC was 647. So if we just don't delete anything, it will be 647. If we delete previous experience, it will be 645.57. That's the smallest number, right? Next one was beginning salary, 645.59. And based on that, R will delete the most useless predictor, which was previous experience. So when we got rid of previous experience, then the AIC is 645.57, right? And then on top of this, if we further exclude beginning salary, the AIC still reduces. If we get rid of anything else, AIC will increase. We want the smallest AIC possible. So R will run a model without these two, where we have only 3 variables remaining. And this had the smallest AIC, because if we add or delete any other variables, it'll just increase our AIC. AIC is the criterion that statisticians use a lot to decide what is the best model possible. So then the final selected model will be shown, the summary will be shown. So the final selected model is predicting job satisfaction by these 3 variables. We had a multiple R square of 66751. So 67.51% is actually smaller than, where is it? 67.52, right? That was 0.1% smaller. But when we compare models, we look at the adjusted R square, which kind of penalizes for just adding another predictor, because R square will only increase if we add predictors. It will never decrease. So we're checking the economy or efficiency of adding another predictor. If we look at the adjusted R square, the 3 predictor model was 67.01, while the 5 predictor model was 0.6668, right? So the 5 predictor model had a smaller R square, adjusted R square, compared to the 3 predictor model. So it means that just using these 3 predictor is more efficient, economic, parsimonious way to predict job satisfaction. And the relations remain the same, that job stress was the highest coefficient value, followed by performance and current salary. And the p-value was in the same order as well. Job stress had the smallest p-value. Okay, so we found that the 3 predictor model is the best to predict job satisfaction based on our sample. And now let's move on to a more practical approach to this. Okay, so if you got this regression model based on a really good data, let's say, what do you do with this? What you do with this is to predict other employees' job satisfaction based on the information that you, based on the linear model that you have. So I provided you the Excel predictor command for you to run. It's using Write Excel and Open Excel. I already have these installed in my RStudio, so I will just copy and paste from here. But you guys can copy and paste everything if you haven't installed these packages. So I will copy and paste everything from here. And basically, this is a command to create a predictor Excel file. So I will show you how this works. So when I run this, what it's going to do is that it says it created an Excel file for me. It made an Excel file for me. So I go to the files folder, click the home button, and boom, we have a new Excel file created by RStudio. So I will open this file, and this is how the file looks like. It's currently showing us the intercept. When all values are 0, this is mathematically needed. Okay, so current salary was in thousands, right? Well, let's say a person is receiving $60,000, and their job performance based on the 45% scale was about middle, like 23, and their stress level was about 23 and on a 45 scale. Then the predicted job satisfaction is 20.822 out of 45, right? So this person will be kind of moderately in the middle level satisfied, not very happy, right? Let's use these numbers. Current salary is 50,000, performance was 10, quite low performance, but their stress level was 5. This person had an even higher job satisfaction. That's probably because the stress level was very low. What if this person was a very high performer, but their job satisfaction was, but their stress level was like very high? Then still this person will not be that happy. But if we can drop this person's stress level to 30, then or even 20, you can see how drastically their job satisfaction will increase. It's going to be difficult to increase their job performance until you provide additional job training and things like that, right? But if we would drop this job performance by tens, you'll see how it drops job satisfaction, right? And if this person is moderately performing and their stress level is quite low, and if we pay them a bunch then you can see that their job satisfaction will increase. A very low the very low stress will also increase job satisfaction, and increasing their self-efficacy based on their job performance will also increase. It went over 45, right? So we can see the relations, and you have to know that this is actually um, how firms, companies predict their whatever outcome they're looking for. If they have data for their revenue, let's say if they have data for optimal number of visiting patients for a hospital, if it's for insurance companies outcome, whatever outcome you have, if you have a regression model that has a high predictability, you can punch in the numbers based on future, let's say we have this model based on all of our employees and we have a new employee. We know how much we're going to pay him. We kind of understand their job performance and their stress level. Then we kind of can predict their job satisfaction. Why is job satisfaction important? The person will have less intention to move or turn over, move to another company, resign, things like that, right? And it's important that your employees are satisfied to maintain a good company culture, right? So you have to be able to apply these knowledge. If you have a linear regression model that you analyze, you can work on predicting outcomes based on data for future outcomes. So this is why I provided you this command so you can create your own predictor. All right. So let's move on to our project now. Getting back to our Aggie football attendance data. We already have this loaded on our library, so let's change our data file into this one. And then we're going to run a linear regression model predicting attendance and also flourishing well-being based on all other variables, all other 7 variables. And we're going to ask R to report the regression model for attendance and regression model for flourishing. So let me run this from line 92. Let me run this. And you should have 2 regression model summary reported. The first summary is predicting attendance intention, right? Attendance intention, for attendance intention, person's agreeableness, team ID, and student involvement were the statistically significant predictors, which were non-zero. And before we look at that, of course, we have to look at the F statistical significant with the R square value of 28.62% explaining the outcome. Looking at Flourish had more variances explained by the 7 variables, which was 48.28%, and the F value was significant with a very small p-value. In this case, we had more variable significant compared to the attendance model. Extroversion, agreeableness, state hope, and student involvement, and team ID very closely to 0.05. We had 5 predictors. Intercept is just telling us that the intercept is non-zero. So this doesn't mean a lot. What we're interested in is the statistical significance of the predictors in our case. So we saw that. So it makes sense, right? We plotted these variables before when you ran correlations in our previous module. So we already did step 1, fitting a linear line on a scatter plot of variables. We compared the linear line with the mean, which was by looking at the F statistics, the overall model significance was significant. It was better than just using the mean. And how much variance was explained compared to the mean is that 48.28% was explained additional to the mean, additional to just using the mean. And then we looked at each predictor's effect on Y, on flourish in this model. And we saw that 5 predictors were significant. Looking at the coefficient value, state hope had the largest coefficient. So while holding other variables constant, one change in state hope had the highest change in flourishing. And the p-value was the smallest. So later when you answer the answer sheet, you will have to decide what you think is the strongest predictor for whatever outcome that you're looking for, because you guys chose either attendance or flourishing, and you guys came up with a lot of predictions based on existing literature and your speculation and prediction, right? Okay, so now let's run additional activity is deciding what is the most statistically fit model using stepwise regression. So I'm going to copy and paste these commands. And it's from line 105. So we're just using stepwise for both attendance and flourishing and gonna report the summary of both. Let's run these models and you should have 2 results. Let's look at the stepwise for attendance first. So the AIC value for our model with all the predictor was minus 81. So we're looking for the smallest value, right? So when we deleted flourish, it showed the smallest AIC. Smaller than minus 81 was small, minus 82, right? So that's what R will do. Get rid of flourish first. And then we didn't have a AIC value smaller when we deleted or added, got rid of or added any other variable. So keeping this 1, 2, 3, 4, 5, 6 predictor model show the lowest AIC. So in this case, we conclude that for predicting attendance intention, we just run a model without flourishing. Then when we look at the stepwise reserve for flourishing, the AIC was minus 403. And only one variable had a smaller AIC than the 7 predictor model. So after we got rid of attendance intention, then no other model by deleting or adding predictors had a lower AIC. So we also conclude that the 7 predictor model is the best fit for attendance intention. And you can see that when we look at the summary for attendance, we have agreeableness, student involvement, and team ID, 3 variables significant. If we compare this with the 7 predictor model, this had agreeableness, student involvement, and team ID as well. So the patterns are the same. But when we compare the adjusted R-square, the R-square will drop every time you get rid of a predictor. But if we penalize adding or getting rid of predictors, we look at the adjusted R-square, and we can see that the adjusted R-square of 0.2732 is higher than 0.2721, right? A very slight change, but still a larger adjusted R-square. So we can see that getting rid of flourishing in our attendance prediction was a more effective parsimonious model. And all same for flourishing, we had extroversion, agreeableness, state hope, and student involvement significant. Team ID got insignificant, so that's very interesting to me, because it was very slightly significant in the previous model. But still, when we just look at the adjusted R-square got up to 0.473 4 from 4726, right? So there was a slight increase in adjusted R square. So there were a lot of based on the shared variances, team ID's unique variance got insignificant. But that's the most statistically significant model. Okay, so you learned how to run simple and multiple regression models. Later on, you will learn that designating mediation and moderation effect could find a significance of some of the insignificant variables because it's just not a linear. It's not just partial correlations that we should look into when we predict variables, and because linear, mediation and moderations can reveal some of the effects that are not just shown when we just put all the predictors together in predicting one outcome. Okay. So for example, if team ID would have an interaction effect with another variable, while team ID decrease, it could affect another variable to increase on their effect on flourishing or attendance or vice versa. So running moderation and mediation model is very effective and important in terms of model specification. So you'll learn more of that in our following modules. But this week, make sure you learned how to run correlation and visualize pairwise relationship into scatter plots to understand that there has to be a linear relationship even when we just look in with our bare eyes to run any regression model. And then you learn how to run multiple and simple regression models. After we fit a linear line on a scatter plot of variables, you learn how to look at the overall model f-test, which tells us if it's just better than just using the mean. And you learn how to interpret the R square, which tells us how much percentage of variance of the Y outcome is explained by predictor or predictors. And you also learn statistical ways to identify what is the most parsimonious model by using stepwise regression, which use AIC method, which also is consistent with the adjusted R square values. The model with the highest adjusted R square value will be the most parsimonious model. And you also create an Excel-based predictor to predict job satisfaction. And the final step for you is to answer this regression answer sheet. So if you look at this answer sheet, you're going to discuss if there were any difference in the R square and the adjusted R squares of your stepwise model compared to the standard model. I told you that R square always drops when you get rid of a predictor, but adjusted R square might differ. Write your observations here and report your most statistically significant model reported in your own words, and interpret the coefficient estimate for each predictor included in your final model. And then you're going to decide which IV was the strongest predictor for your DV. There is no absolute answer for this, so I am just really open to any type of interpretation or predictions based on your own insight, based on your analysis using the Aggies football data. And the last thing is to copying and pasting your R console output by selecting all, copy and pasting Control C and Control V to here, and that will be your progress report for this week. All right, so I want to emphasize again that understanding regression modeling is the essence of any type of data analytics out there, because most of the analysis is based on regression type of approaches. I really simplified the steps for you. First, you look at the scatter plots to see if there's any linear relationship. Then you run a regression, and then you look at the overall model results by comparing the linear line with the mean. So the f-test will tell you if your linear line is any better than just using the mean. If you have a smaller p-value than 0.05, then it's different, it's better. And looking at the R squared, it will give you some practical significance of how much percentage of variance do the predictors predict on the outcome. And then we look into the individual predictors, estimates, and p-values. If the p-value is smaller than 0.05, usually in social science, we conclude that there's a statistical significance that the estimate, the linear relationship is not, at least not zero. So we're then very confident that we should use such predictors to predict whatever outcome we have. So for flourishing, 1 point increase in state hope predicted 0.30289 increase in a flourishing a person's well-being. 1 point when holding other variables constant, when extroversion, agreeableness, preseason hope, and involvement in team ID are the same across other people, then state hope, 1 point state hope increase predicts 0.320989 increase on flourishing well-being. If there's 1 point increase in agreeableness, then when holding other variables constant, we predict that there will be 0.18202 increase in flourishing. So that's how you interpret each individual's slope, and that is how you can run a regression. And you can modify the regression commands by including that you want standardized coefficients reported on your summary results and things like that. And like I told you, generative AIs are a very good tool to modify your codes and commands in R. So I really hope you guys get efficient and competent in using these tools, as these are now becoming being able to use these languages is a very strong skill set nowadays in the industry. Okay, that is the end of the video for today. It's kind of long, but I kind of went through a lot of things about regression because I can't emphasize enough how regression is kind of really the basics before we move on to other modeling techniques. Okay, thank you for watching this video. I will see you again in our next video.